Okay, today is Thursday, April 8th, 9th, 10th, 11th, I think. I'm filming this on the night. And we are looking at the Chapter 3 review in chemistry class, which is page 468, starting with number 51. 52, 56, and on to 90. That list is in Google Classroom. You know how to find that. So let's take a look at these. Question 51 says, if two variables are inversely proportional, what happens to the value of one as the value of the other increases? If they are directly proportional, one goes up, the other one goes up. If they're inversely proportional, one goes up, the other one goes down. One goes down, the other one goes up. You know that from math class. And an example of an inverse proportion in regards to chapter 13 on gases is Boyle's law. If you have something like this, up here somewhere there's something like this, I decrease the volume and make the volume less, the pressure will go up enough to where I can shoot this cap off here. If I increase the volume, the pressure goes down to the point where I can pull that out of there. Number 52. If two variables are directly proportional, what happens to the value as the other one increases? So here you have things multiplied so that in number 51, with an inversely proportional, so one side is established or constant. If this goes up, that has to go down, or if this goes up, this has to go down. Inversely or directly proportional, you're going to have two ratios, two division problems, and you'll do a proportion just like you do in math class. And two examples that we saw with that, in regards to chapter 13 anyway, is, I don't have it written in here, but you could have, let's say temperature be down here and pressure be up here. As you increase the temperature, the pressure increases in a sealed can. So if this side stayed constant, if this goes up, this goes up. Or in the case of volume and temperature, if the temperature goes down, the volume has to go down, like a balloon in a freezer. Okay. All right, let's go on. That's enough of that. 56. A weather balloon is filled with helium. It's got a volume at 50,000 liters at almost an atmosphere. 32 Celsius. You release it, it rises to where the pressure is less, 0.72 atmospheres, and the temperature is -12, so quite a bit colder. So let's use the combined gas law here, which is sticking the temperature under here, and just put the temperatures in. Use Kelvin on the temperatures. If you don't, and you use Celsius, you're making the choice to miss them. Which doesn't seem logical to me. So the easy time to use the combined gas law is if you have a gas and the conditions have changed. And this is a classic example of a weather balloon goes up, the pressure goes down, temperature goes down, volume is going up. Well, decreasing pressure is going to want to make it expand, decreasing temperature is going to make it contract. So it depends on what the numbers are, so which one happens. So if you put the initial temperature and pressure as 305 Kelvin, because you have added 273 Kelvin to the temperature, which would be what, 25, 6, 7, I don't know, 32, I think. 32 Celsius. It's 305 Kelvin, whatever they said. In 0.995 atmospheres, you had 50,000 liters, and you've dropped the pressure down and dropped the temperature. What does V2 come out to be? Well, you have to bring this up here and multiply times 262. Now, make sure, if you didn't already know that, you know that now. You have to take this down here and multiply it down here, so you're dividing into 0.720 atmospheres. So from the top it goes to the bottom, from the bottom it goes to the top. And then you multiply all the tops, write it down. Multiply all the bottoms, write it down, and then divide when you're done. And when you do that, you get 59,100 liters. Okay, the next one is number 59, the temperature changes here. What is the pressure of a fixed volume? So volume on this next one is not a factor. So if you have a steel container, it's not going to get bigger or smaller unless it breaks or something. Glass container. So you do have to use reading comprehension in this test. You know, if it's a steel container or a glass container, there's something that's not going to flex, the volume is constant, it cancels out. So pay attention to that. Fixed volume, hydrogen 30 Celsius, pressure 1.11 atmospheres at 15 Celsius. So I can probably use the combined gas law and cancel volume out. That's it. Doesn't change. Okay. Something's wrong. Oh, I already did 58. Nope, that was 56. Okay, we're on 59. I was talking about 58. So let's jump to 59 since we did that. 59, volume's going to cancel out, and you end up with this. You put 1.1 atmospheres here, 288 Kelvin here, temperature 2 is 303 Kelvin. You have to use Kelvin, not Celsius. So this was 30 Celsius. This was 15 degrees Celsius. Don't use the Celsius. Don't use a degree symbol with Kelvin. I won't freak out if you do, which you're not supposed to. Then you solve for P2. We're going through work on this. I told you to use Celsius, not Kelvin, a couple times, and pretty much people decided to ignore me and missed them anyway. Okay? So you're going to bring this out of the denominator, put it up here and multiply, and you get 1.17 atmospheres. Backing up to 58. Another hot air balloon. A sample of air occupies 2.5 liters at a temperature of 22. Convert it to Kelvin, which is 295. Because you're adding 22 and 273. What volume will be inside at 43? Assume the pressure remains constant. Okay, so in that case, on 58, if the pressure stays constant, cancels. And the temperatures are 2.50 liters, 295 Kelvin, and 316 Kelvin. You're going to bring this up here, out of the denominator, multiply it here. Multiply those two, divide by 295, you get 2.68. Next. Number 60. You got a sample of nitrogen gas transferred to a larger flask. You gotta look at the picture there. Now that flask is made of glass, so the containers don't flex, but you're going from a smaller container to a large one, so you did change the volume. And we've got a 500 milliliter and a 750 milliliter, both of them are nitrogen. You got a pressure in the small one that's going to be less than the larger one, probably, because it's expanded so much. But the temperature went up, but it only went up a little bit. So I would guess you're going to have a lower pressure when this is done. That was 59, which we did out of order. Okay, so use the combined gas law because you're changing conditions here. Your initial pressure was 108 kilopascals. Your initial volume was 0.5 liters. You can use milliliters in this case because milliliters will cancel, and so will liters. So why convert it to liters? Because just use liters on the volumes. Since we're going to use 22.4 liters per mole, and making that conversion if you already having things in liters is just going to be easier. It works without it if you don't convert it. This is 283, this is 294, so this is 10 degrees Celsius and this is 21. Okay, you're going to bring this up here, multiply. You're going to take this down here, multiply down here, so you'll end up dividing when you're done. Multiply the tops, write it down, multiply the bottoms, write it down, then divide, and you're solving for P2. Comes out to be 74.8 kilopascals. Number 60 is complete. 63, you have a mole of gas at STP. The easy way to do this one is ideal gas law. We're not changing conditions on this one. It does ask for mole though. Oh, I guess it's not even that complicated. We don't have to do the conversion necessarily because it's 1 mole at STP. That's 22.4 liters. 1 mole at STP is 22.4 liters. And that's for any gas because the particles of the gas are minuscule no matter how big they are if they're still a gas. And so they just don't make up enough volume compared to the volume of all the empty space that's in there to count, to contribute anything. 2 moles is going to occupy twice that much, 44.8 liters. Okay, number 66 says what units must be used to express temperature for the ideal gas law? You're using Kelvin, and the reason you're using Kelvin is you want on your graph the volume to drop to 0 for the gas when the temperature drops to absolute 0. If you have Kelvin temperatures on that, you're going to be, I don't know, something like your y-intercept is not there. I think it would graph something like this. So you want that to graph down to the origin. Okay, I'll finish up the rest in the next video.